Hola a todos. Good morning, everybody. So this is the second part of the course we started yesterday. Yesterday we introduced those carbon structures, fullerenes, nanotubes, and graphene. We stressed the importance, the interest of those different nanostructures, and we studied quite in depth the structure and the defects that you can find in those objects. Today we will mainly focus on how to make those objects, the different methods of synthesis. Can you hear me well? Yeah? And we will then focus on the main synthesis method presently used for the synthesis of graphene and carbon nanotube, which is called catalytic chemical vapor deposition, which is a special case of CVD, a technique that some of you may already know. And after that, we will go to things more fundamental, try to understand some things concerning the growth mechanism of those objects, knowing that this is still an important subject of investigation. By that I mean that we don't know everything, but I will try to let you know about what we know quite well. Okay, so this is the plan for the next 2 hours, and we will start by a description of the different methods that can be used to grow carbon nanotubes, graphene, and fullerenes. The techniques are divided in 2 types. The first type are called high temperature methods because they involved temperatures as high as a few thousand degrees C. Okay, this is quite high. To obtain such temperatures, you need special technique like using a laser, a pulsed laser, or in some cases a continuous laser, to sublimate, to vaporize carbon atoms from a solid carbon source like graphite, and then during cooling of these sublimated atoms, there may be new carbon forms that will form, including fullerenes, including nanotubes. Okay? This laser ablation is the original technique used by Smollet, Curl, and Kroto for the discovery of fullerenes, the first molecules of this family of carbon nanostructures. So this is the original technique. We will see it in detail later. The second technique is arc discharge. In this case, a high temperature is obtained by putting side by side 2 electrodes made of carbon with a small gap in between, applying a high difference of potential between the two in order to induce an electric arc between the 2 electrodes in the gap. Because of this electric gap, you create a plasma, a very high temperature plasma, reaching temperatures as high as these values. So again, in this case, due to the very high temperature induced by the electric arc, we will sublimate carbon atoms from a carbon source, graphite as well, and during cooling, new carbon forms will form. Okay, so here we form reactive carbon atoms by sublimation at high temperature of a solid carbon source. We need to go that high because graphite has a very high sublimation point. Okay. There are 2 different ways to do that. You can mix catalyst together with graphite, and this catalyst will be sublimated together, and during the cooling you will form also small metal catalyst particles, and thanks to this you will form a special type of objects, which are the single wall nanotubes that we have already discussed yesterday. Without catalyst, this is the original method, what you will obtain is either fullerenes in some conditions or multi-walled nanotubes in other conditions. But you will never obtain single-wall nanotubes if you do not mix a catalyst together with the carbon source, graphite. Okay? The second type of techniques is called medium temperature methods because they involve temperatures in the range of 500 to 1000 degrees C. Actually, there is now only one main method in this category, and this is the technique called catalytic chemical vapor deposition. What is different here? This is first the carbon source. This is no more graphite, this is no more a solid source. The source is a vapor. Here we are going to decompose a vapor or a gaseous carbon-bearing molecules such as acetylene or methane or ethylene, and we will decompose that not only thermally, just with increasing the temperature, but thanks to the use of a catalyst. The catalyst, as you already know quite well, allows to decrease the activation barrier for the reaction. It does not change the thermodynamics. It is just here the catalyst to make the kinetics faster by decreasing the activation barrier between the initial state and the final state. Okay, this is the purpose of a catalyst. And we will see that in detail. Once we have decomposed the carbon-bearing molecules, we got reactive carbon atoms. And the carbon atoms can coalesce at the surface of the catalyst, and they can make different type of materials. So in this case, there is always a catalyst, but the catalyst may be in different forms. They may be as nanoparticles, but there may be also like a very thick layer of metal, of catalyst, deposited on a substrate, or even just a film of metal, like an aluminum foil or a copper foil. If you use nanoparticles, you will be able, by a template effect, we are going to talk about that later in detail, you can obtain nanotubes, either single-walled or multi-walled. If you use a thick layer of catalyst, then by this template effect, you will not grow a tube, but you will grow something flat, that is graphene. Graphene either with a single layer of graphene, or maybe, in some cases, several layers of graphene stacked together. Okay, it's important also to mention that presently graphene can be quite easily obtained not by these high temperature techniques, but by using a natural material, which is graphite, and to exfoliate graphite, it means taking each plane of graphene out of graphite one by one. Okay, there are different techniques to do that, especially in liquid suspension of graphite, and this will be discussed and presented in detail during the course of Alain Pénicaud next week. So I will not talk about this important technique of preparation. This is not synthesis, but it is important that you know about this method of preparation of graphene, because it allows to make a lot of material and at a low cost. Okay, now we are going to describe these techniques, starting by the high temperature ones, and then we will go to the medium temperature one. First technique is laser ablation. As I already said, we are going to use a laser to heat a solid carbon source, which is a piece of graphite, heat so much that carbon atoms here at the interface will sublimate, become vapor. then we will form like a cloud of carbon atoms, and this cloud will move because of the flow. Here we got an argon flow in this direction, and during this time, during this travel, it will cool down. The carbon atoms will cool down, and new solid carbon species, solid carbon structures will form. To collect them, there is here a piece of copper which is water cooled in order that its surface is sufficiently cool, cold to make the carbon structure coalesce and stay at the surface of this collector. And this is where we are going to collect the carbon materials that has been formed during cooling of this cloud of carbon atoms. In addition, to improve the control of the cooling, we may add a furnace around the reactor. For now, it was just a cold wall reactor. But now, if we use a furnace around this here quartz tube, then we can control also the temperature of the walls and have a much better control of the temperature in the reactor. Okay, this is no more cold wall reactor, it's a high temperature wall reactor. Okay, this is the first technique. Second technique is also a physical method. We will make in this reactor, we will put helium, and there are two electrodes facing each other, and we are going to apply a difference of potential between those two electrodes, and when the electrodes are close enough, then an electric arc will create, and this will create a plasma that you can see here. And this plasma is a very high temperature ones. What will happen is that this mobile anode will be consumed, just this one. The cathode will not be consumed because the plasma is oriented. There is a bombardment of ions from the cathode to the anode. It means that the anode is etched away, it is consumed, but the cathode remains the same. To keep the distance constant between the two electrodes, because there is a consumption of one electrode, you need to have a mobile electrode. This is why you push the anode toward the cathode all along the synthesis in order to keep the gap constant, to keep the electric arc. Because if you have a too large gap, you will lose the electric arc and you will stop the plasma. It's the same as here. Then you will have cooling of carbon atoms. In this technique, there is no water-cooled collector, but very often there is like a tubular form around the central part where carbon structures will deposit, and then you can collect them at the end. Okay, so both techniques use sublimation of graphite, and in both techniques the carbon nanostructures form during cooling. What are the obtained materials? Here are examples. You can obtain fullerenes, you can also obtain nanotubes. Those nanotubes can be considered as high quality ones. By high quality, I mean with very few defects. The fact that we have a very low density of defects is mainly due to what, according to you? Why is there so few defects in the materials formed in these techniques? No idea? Es Merida or Kumana? Merida? Kumana? Any idea? Okay, we talked about that yesterday, a bit about how to prevent creating defects. And the fact is, for a carbon atom, ah, an answer. Okay. This is the answer? No answer? No answer? Okay. Bon. Yesterday we said that to obtain a well crystalline material, we needed to give atoms time and energy to go to the most stable position. Here we have a lot of energy because we work at very high temperatures. It means that the carbon structures, even if they do not form the most stable structure at first, due to the thermal energy, they will rearrange, restructure very quickly and go to the most stable state, the most stable structure, which is without defects. Okay? So this is why we have so few defects in these structures, because we work at high temperature. We will see that when using medium temperature technique, a real problem is to make structures with not too much defects. It's more difficult. It's possible, but it's more difficult. Here, it's like intrinsic. You do not have to do anything special. They are always high quality. The length can be tens of microns long. The multi-wall nanotubes, as you can see here, are very straight. Their diameters are between outer diameter is between 5 and 30 nanometers. And as I said before, if we add some catalyst like nickel or cobalt together with the graphite, then we will observe experimentally that the obtained products are no more multi-wall nanotubes or fullerenes, but single-wall nanotubes as observed on those pictures. Here you see a bundle of several single-wall nanotubes packed together as we already saw yesterday.
Why the structure are like this kind of bend and kinks? This is a more stable configuration for when you growth nanotubes. On your left. Yeah. Top one, yeah. Both of them.
Okay. So about the shape of the ropes here, the fact that they are bent, as you see, it's bent here, and here also it's also very bent. Actually, it's a characteristic of single-wall nanotubes. They are very flexible. They are very flexible because there is just one layer of atoms as wall, so it's very easy to bend it. In some cases, it's like I don't know the word for that, but when you drink in a glass of water with a pipe, okay, okay. I will say a pipe. Pitilio, okay. Well, with that, you can easily bend it, and it will make like a kink. Okay. This also is possible with nanotubes, but here, okay, it's not observed. But I mean, it's an extreme case of bending of single-wall nanotubes. They are extremely flexible because there is only one wall. It's different with multi-wall. There are several walls together, and this gives rigidity to the structure. They are very rigid. If you bend them, you break them. Okay? And this is due to the mechanical reinforcement between the different layers. So these ones are very straight, very rigid, and those ones are very flexible, and depending on the environment, they can be bent. That's it. Okay, so there's different types of materials. Now I move to the, okay, there's a question from the audience.
I have two questions. Exists some difference between the catalyst if I use nickel or cobalt in the way for obtain this carbon nanotube? And what is the difference between the performance about the two techniques, ablation laser and arc discharge, in order to obtain more or less carbon nanotube?
The first question is about the effect of the nature of the catalyst on the obtained product. So actually there are many effects in terms of yield. The elements, the catalysts giving the best yields are usually nickel, cobalt and iron. In addition, it was discovered like 10 years ago in Montpellier that if you add some amount of other elements like yttrium or lanthanum, you will increase the yield by several orders. This is not well understood why yet, even now. Okay, but experimentally, I can say that the best elements are usually nickel, cobalt mixed with an addition of another lanthanide element. And also, when you change the nature of the catalyst, you will change the diameter of the nanotubes. For a given here, all the nanotubes do not have the same diameter, but there is an average diameter, there is a distribution of diameters, and if you change the catalyst, you will shift this distribution to a higher or lower average diameter. Okay, so for instance, if you use platinum as a catalyst, you will have much larger diameter nanotubes. Okay, and there was models to explain that due to the difference of eutectic point, but this also is not well understood yet. You will see that later when we talk about understanding the growth mechanism, understanding fundamental things, we'll talk a lot about CCVD, because this technique rapidly went the most used ones, and those two techniques, high temperature techniques, were kind of abandoned. For this reason, there are still many question marks about the growth mechanism of those structures using high temperature methods. Okay? And the second question was which technique is the best, arc discharge or laser ablation? The fact is that laser ablation was the initial technique, but it's very costly. It's very expensive. You need a very expensive laser to induce such sublimation. You need very special apparatus. On the contrary, arc discharge, this is really easy to make, and it's very cheap, and you don't need this special laser. So this is a much more democratic technique, but let's say that there is more byproducts, carbon byproducts, like amorphous types of carbon. Here it's more controlled, but very expensive. Here it's more democratic, but more contamination. Say again? Which one produces more carbon? More. Okay. In terms of purity, this technique makes more. In terms of quantity, these techniques, you can make much more kilograms of nanotubes per day. Okay? Higher purity, larger quantities. Okay, now I move to the second type of techniques, which is catalytic chemical vapor deposition, working at medium temperatures between 500 typically and 1000 degrees C. We are going to explain this long word. First, I think it's very important for a scientist to use proper words. Words are very important and very useful. Using the proper vocabulary is important, and when defining a new word, it's important that each word has a meaning. So here, what are the meaning? How did people come to this word? So first, we have deposition. So it means a deposition technique is a method to prepare a layer, and this layer is usually needs a support. And this is related to all we know about thin film technologies, such techniques. So deposition, we are going to make a layer. Vapor deposition, what does it mean? It means that we are going to use a precursor to make this layer, which is a vapor or a gas. And this is by contrast to other type of deposition like liquid deposition, where we start from a liquid precursor, for instance using spin coating of a dissolved resin in a solvent, for instance. Chemical means that the precursor will be chemically dissociated, chemically cracked, and this is by contrast to the techniques called physical vapor deposition, like vacuum evaporation or sputtering that people doing microelectronics know very well. And this chemical vapor deposition, also named CVD, is a very important process both in the lab and the industry to prepare layers and support. And you will find this word very often in the literature. Now, when nanotubes came and graphene came, a new type of CVD was invented, adding a catalyst inside the reactor. What is the purpose of the catalyst? Here the catalyst helps cracking. Cracking of the precursor is assisted by a catalyst. It implies that the dissociation of the precursor is localized at the surface of the catalyst. The decomposition is not everywhere in the gas phase, everywhere on the surface. It occurs only at the surface of the catalyst. So you've got a localized dissociation, a localized cracking of the molecule. And this is important to prevent the formation of byproducts, like amorphous byproducts you do not want to form, and to have the growth localized and on a special point. This is by contrast to what is called self-pyrolysis. Self-pyrolysis, lysis means cut, break, pyro is heat, and self by itself. So it means breaking the thermal decomposition of the molecule by itself. That it means without catalyst assistance. Okay, just understand the origin of this name. How is it like? So actually you see here a picture of a CCVD reactor. You've got a furnace, usually a tubular one, with a quartz tube acting as a reactor, passing through the tubular furnace. You can see the long quartz tube here. Inside the quartz tube is put a catalyst, usually deposited on the support, inside a vessel, a boat, inside the reactor. This is heated by the furnace, the oven, and then to grow carbon nanostructures, we will introduce carbon containing gases, like here acetylene, but you can use many other types of carbon bearing molecules as carbon precursor, like methane, like ethane, ethylene, acetylene, carbon monoxide, ethanol, benzene. Many types of carbon precursors can be used. Okay, usually there is also another gas called a carrier gas, just to dilute the reactants. It's an inert gas, like nitrogen, like argon, like helium. Okay, What is important also for these techniques is to remember that the metal, the element used to crack the catalyst, so is termed catalyst. To crack the precursor is termed a catalyst, but it has also a template effect. So template, I think this is clear for everybody. The term template, so it means that this object will help to make a special shape. The shape of the object, of the catalyst, will be reproduced by the growing nanostructure. So this is called the templating effect. So it's a very important effect in nanoscience, in nanofabrication techniques, because how to make nanometric objects. Using the template effect, if you already have something which is nano, you can make something else which will also be nano. Okay, different types of templates. If you use nanoparticles, you will get nanotubes. If you use a thick and flat layer of catalyst, you will get graphene, as we already mentioned in introduction. Now, this technique, CCVD, is the most used technique to grow graphene and carbon nanotubes. To grow fullerenes, arc discharge is still the most used technique because you cannot make fullerenes with CCVD. But CCVD is now the most popular technique to grow carbon nanotubes on graphene. Why? Because it's scalable. You can upscale for an industrial production. It's a low temperature technique, so it means it's less costly. And also, you have much more controlled conditions. For instance, the temperature in the reactor can be the same all over the reacting part, which is not the case for arc discharge and laser ablation, since the objects are formed during cooling. So it's difficult to control cooling. But here, since the temperature is constant, is the same everywhere, we've got something which is much more controlled. Also, you can, from the beginning, control the size of the catalyst particles, while in arc discharge and laser ablation, the catalyst particles are formed in situ, inside the reactor. So it's even more difficult to control their size. So here, you can decorrelate. You can control things on one side, control other things on another side. You don't have to control everything together. Okay? Okay, examples now of what you can obtain using CCVD. For instance, you can obtain here like a forest of nanotubes, a very thick and dense forest of aligned nanotubes. What do you see on the left top picture? This is an SEM picture. At the top here, this is the support. It's usually silicon oxide. And perpendicular to this support, nanotubes have grown like a forest, like a carpet, like grass. It can be very thick, as you can see here, 36 microns, but much thicker forests have already been grown, having several millimeters of height. So this is an example of what you can get, nanotube forest, with tubes growing perpendicular to the substrate, to the support. Another example is the growth of nanotubes parallel to the substrate. The first example is this. You see nanotubes, and just below in the background is the support, which is usually also silicon oxide or silicon. Here you see that the nanotubes are very well aligned, and they are also quite long, several hundreds of microns. The nanotubes in this case were aligned by the gas flow that you have seen here, used inside the reactor. So in special conditions, where you have a proper balance between this forced convection induced by the flow and the natural convection from bottom to top, which is also called buoyancy, this natural convection toward the top and the forced convection toward one side, then if you have this proper balance, you can have nanotubes growing in the gas phase and oriented by the gas flow. This is called kite growth. Kite is a tool that children use on the beach when there is enough wind. So I don't know the word in Spanish. Kite. Kite, you know? Cerf-volant. Parapaillo. Oh, okay. So this is called kite growth, oriented by the gas flow. Another way to orientate the nanotubes during the growth is to use a special support which is crystalline like quartz, and on some special faces of those substrates you can have an orientation of the nanotubes along a special lattice direction of the support. So this is a growth which is lattice oriented or lattice aligned. As you can see here, many nanotubes, very dense, all aligned along the same direction, along the same lattice direction of the support. Question?
You can call this one on the bottom part, you can call like a epitaxial growth, or kind of?
From my point of view, I would not call it epitaxial growth, because there is no epitaxial reproduction of the crystal structure of the support here. Okay, so it's not crystal epitaxial crystal growth. As compared to what is usually considered as epitaxial growth. Okay. However, there is a reproduction of the waves at the surface of the substrate. So it's like an undulated layer, the substrate, and the tubes goes into the bottom part of this undulated layer, because this is where they have the maximum interaction with the substrate. And the interaction is van der Waals type interaction. They maximize their van der Waals interactions in those bottom part of this undulated surface. But not all surfaces have this like shape at the atomic scale. So this is very, very thin waves. It's really at the atomic scale. Okay, another example here is the growth of graphene on copper. You see different patches here. Those patches are graphene deposited on a copper layer, a thick layer of copper. And the size is a few tens of microns of those graphene islands. Okay, so those were examples of what you can grow. And now we are going into more details of this technique, catalytic chemical vapor deposition, because it is the most used technique both in the lab and in the industry. So first, about chemistry. What are the elementary steps, the elementary chemical steps that one should expect, one should consider when mixing those elements, mixing a carbon-bearing molecule together with a catalyst surface and increasing the temperature? What will happen? You've got this precursor. As an example, I took methane. This methane, to react with the catalyst, has to diffuse in the gas phase. So this is also called mass transport, gas phase mass transport. It diffuses to the surface. Now it is close to the surface. If it has a good sticking coefficient, it may adsorb on the surface, but also once adsorbed, it could desorb. We have an equilibrium. an adsorption-desorption equilibrium between methane at the surface, adsorbed on the surface, and methane in the gas phase. Then, because we use a catalyst which is good for dissociation, for assisting dissociation of carbon-bearing molecules, we can have this dissociation and completely, fully dissociate the carbon-bearing molecules into carbon and other molecules like hydrogen. Hydrogen usually desorbs after forming H2 molecules. Then, to make a carbon structure with several carbon atoms, you need those atoms to meet. So you need them to move, to migrate inside or on the surface of the catalyst. So there are two types of migration, diffusion, that can be considered. Just
porque les interesa a la gente ir a ese tipo de cosas. De manera que eso lo tenemos que conversar pues para seleccionar 3 títulos. Y no solo.
No? Okay. Sorry. So I keep going. We can have either surface diffusion or bulk diffusion. Then those carbon atoms can meet and they can form large islands of carbon by creating sp2 bonds, and then a graphene layer or a nanotube can grow from these elementary atoms. So this is just to give you an idea of the different reactions, different chemical reactions involved in order to grow at the end a carbon structure at the surface. Okay, now we are going to discuss how to choose the best catalyst, how to choose the best carbon precursor. So this is a general approach that can be used for other chemical reactions. When you want to grow something, which reactant are you going to use? Which catalyst are you going to pick up? Okay? So here, we want to make graphitic structures like graphene, like carbon nanotubes. Basically, their energy, their formation energy is similar to graphite. It's about the same. The formation energy of graphite, by definition, is 0. It's here. If you use other precursors to make those, you want to know if the reaction is thermodynamically allowed. Okay? Being thermodynamically allowed means that you go from a high energy state to a lower energy state. If you look at that, you see that for methane, for instance, its standard free energy of formation is always lower than graphite till a temperature close to 600-700 degrees C. That means, from this diagram, which is called an Ellingham diagram, which is a very important tool in thermodynamics, that it is not allowed to make graphite from methane below 600 degrees C. What it tells us also is methane is a very stable molecule. To dissociate it into graphite and into carbon atoms that can make graphite, you need to go to high temperatures. Other precursors, like acetylene, for instance, are very unstable. Acetylene is a well-known molecule for reacting, very reactive molecule. If you leave it alone for several months or several years, it will react, polymerize, and it can even become explosive. Okay? Acetylene is extremely reactive. The good thing with acetylene is you can use it even at low temperature. Methane, you need very high temperature to dissociate it. Other precursors you can use are ethylene, which is like intermediate between acetylene and methane. Carbon monoxide is a special case because this is you at the beginning of this reaction you got two molecules, two gaseous molecules, and at the end you got only one. It means that the entropy changes a lot, and this is why you have such a negative slope for carbon monoxide. Also, you see that carbon monoxide, like methane, if you increase too much the temperature, then the dissociation of carbon monoxide into carbon will not be thermodynamically allowed anymore. And another precursor you can use is ethanol. And here what is interesting is together with carbon and hydrogen you also bring oxygen, and this oxygen can be useful or not during the synthesis. And you have to take also into account that you bring something else. It's not carbon you bring in. With this carbon precursor you also bring hydrogen, you also bring oxygen, and these are important elements that can react together with carbon. Okay, so this helps to choose the proper carbon precursor, and as you can see, choosing the most appropriate carbon precursor is very dependent on the growth temperature you are going to use. And conversely, depending on the growth temperature, you will use a different carbon precursor. Okay, so this is the first Ellingham diagram. We will see others during the next slides. An Ellingham diagram is simply plotting the standard free energy of a reaction, often of formation, as a function of temperature, to know if a compound is stable, more stable than another one, if a reaction is allowed, such things. Okay, now we move to the choice of the catalyst. Which element should we choose, should we pick up as a catalyst? To understand this question, we should first wonder which are the important functions of this element that we call catalyst. It's important to know that even in the nanotube and graphene community, many people still wonder if using the term catalyst is really appropriate, because many people, by comparison to heterogeneous catalysis or liquid phase catalysis, homogeneous catalysis, consider that the catalyst is an important characteristic, an important feature is that the catalyst is not used during the reaction. It is not consumed during the reaction. You still have the same amount of catalyst at the end than at the beginning. Here we'll see that there is some deactivation of the catalyst for many reasons. But it's also the same in heterogeneous catalysis, in homogeneous catalysis. Deactivation, poisoning is just a very general phenomenon in catalysis. So the answer is yes, it is a real catalyst, and the catalytic act is to assist the dissociation of the carbon precursor. This is why this is a catalyst. But it is not only a catalyst here. And this is the difference compared to heterogeneous catalysis, where you form gaseous molecules or liquid molecules that will desorb from the surface. Here we form solid structures, and they keep on the surface. They are not desorbed. So you need other important functions for this element called catalyst. An important thing is to allow the diffusion of carbon atoms, as we already saw, because we need them to meet and coalesce to form large sp2 lattices. Another important thing is to prevent the desorption of these formed species. We don't want the species to desorb once a first benzene ring has been formed. No, we want to make many benzene rings, many hexagonal rings, linked together to make a long, large, solid carbon structure. So we need the catalyst to keep the formed structures anchored, linked, bound to the surface. But at the same time, the bond should be weak enough to allow new carbon atoms to come in and to be integrated at the frontier, at the interface between the graphene and the catalyst. Okay, so we need like an intermediate bond, not too loose, not too strong. And then we also talked about the template effect, which is very important to decide if we will make a flat structure like graphene or a tubular structure like nanotubes. So here we need a template, we need a special shape, and we need this shape to remain during the growth. Remember that we are at very high temperatures, like 600, 700, 1000 degrees C. At this temperature, atoms move very fast. The mobility is very high. So you should not take for granted that the particle remains the same at 1000 degrees C, remains similar than what they were at room temperature. Okay? But despite these problems, we need to keep this stable at least for the duration of the growth. Points 1, 2, and 3 are strongly dependent of what we call carbon affinity. This means the affinity of an element to bind to carbon. And we will see many examples of how carbon affinity shows up in different reactions. Carbon affinity is important because the higher carbon affinity makes the best catalyst for decomposition. Our carbon affinity is important because a too strong carbon affinity will prevent diffusion of carbon atoms at the surface. And the carbon affinity is important also for an appropriate binding between the carbon structure and the surface of the catalyst. Concerning the last point, point 4, this mainly depends on the thermodynamic properties of the catalyst itself, like its melting point, like its sublimation point, like its wetting properties, its surface tension, and also this wetting not only depends on the catalyst itself, but also on its interactions with the support. These different surface tensions, surface energies of the substrate and of the catalyst will decide the wetting of the particle on the substrate, either having something like a sphere or having something like a flat layer. So we will mainly talk about this point during the last chapter on deactivation, because this is mainly a deactivation problem to keep a stable template. Now we focus on the carbon affinity. Choice of the catalyst. So first point is to have a good catalyst for dissociation. As we already said, being a good catalyst, the essential catalytic act is to lower the activation barrier between the initial state and the final state. Just decrease this activation barrier. That is the energy of the intermediate state between initial and final states. How those elements modify this activation barrier? Actually, you need to weaken the carbon-carbon bonds. And to do that, you need to create a very strong interaction between the adsorbed molecule and the surface of the catalyst. So the higher carbon interaction, the higher interaction between the adsorbed molecule and the catalyst surface, the higher catalytic activity, because you will weaken the CC bond by creating a very strong carbon catalyst bond. How does this, how is it observed experimentally to have catalytic activity? Well, a very useful experimental data is the adsorption energy, also called the heat of adsorption, the enthalpy of adsorption, and the adsorption energy is defined like that. It's a difference of energy between this initial state, that is the carbon-bearing molecule in the gas phase, and the adsorbed carbon molecule. How does this adsorption energy, which gives you an idea of the strength between of adsorption of the molecule on the substrate, how does this physical value is modified as a function of the elements? Here is shown a plot where you have this adsorption energy for different elements, and this is plotted as a function of the position of the central position of the D band of this metal. All these metals are transition metals, D band metals, and as you can see, there is nice correlation between the position of the elements. Gold and silver are on the right of the periodic table, while yttrium, scandium, titanium are on the left of the periodic table. And as you can see, when you go from the right to the left, from the right to the left of the periodic table, the adsorption energy is more and more negative, which means that you have a stronger and stronger interaction between the adsorbate and the catalyst. Those elements, the left of the periodic table, are very good catalysts for dissociation. They will readily dissociate any carbon-bearing molecules when the molecule gets in contact with the surface. While those elements here, like gold and silver, are much less reactive. Sometimes the carbon molecule will not even adsorb on the surface. It will adsorb for a very short time, and it will not dissociate. Here, no adsorption, intermediate case adsorption, but weak decomposition, and here, very strong adsorption and decomposition, dissociation of the molecules. So this value, the heat of adsorption, the adsorption energy, gives you a first idea of the interaction between the adsorbate and the surface of the catalyst. This is a very useful physical value used in heterogeneous catalysis to describe the catalytic activity of an element. So first element of choice. Now, to talk affinity of an element, we can consider whether this element like to make compounds with carbon. That is, carbide compounds. Does this element like to make carbide compounds, or does it never make carbide compounds? This propensity to form carbides is an illustration of the affinity of this element for carbon. Here also we can use an Ellingham diagram for that. We can plot the free energy of formation of carbides for different elements. And the definition of this free energy of formation is given here. It's free energy for this reaction between the metal, the carbon considered as graphite, and here the carbide between formed with this metal. If we plot those formation free energies as a function of temperature, which is again an Ellingham diagram for carbides, we find again graphite here with a free formation of energy of 0. And what we observe is that different elements can form different carbides, and those carbides have different stabilities. The most stable carbides, of course, are the ones here at the bottom, the ones with very negative free formation energies. Here, you also observe that these elements are elements at the left of the periodic table, like before, for the dissociation properties. On the top here, you've got carbides which are called metastable carbides. Why metastable? Metastable means that they are observed, but they should not be observed on a purely thermodynamic point of view. They are just kinetic products. They should not exist. If you give enough time, they will decompose into more stable compounds. As examples, you've got iron carbide, cobalt carbide, nickel carbide. Again, those are elements that are on the right of the periodic table. And in between, you've got elements that are in the middle of the periodic table. So those carbides are sometimes observed, but not for a long time. Usually, they readily decompose into graphite and metal. Okay, this is just the inverse reaction. Not in this direction, but the other way. Okay? Because we have a positive free energy of formation. So this gives you another idea of the carbon affinity of the different elements. Those elements at the left of the periodic table like to bind to carbon, and those elements does not like too much to bind to carbon, but a little. There are also elements that are not present on this figure. Notably, we can cite copper, zinc, which are elements at the extreme right of the periodic table. Those elements have such a low affinity for carbon that they do not form any carbide with them. Okay? So this is another illustration of the carbon affinity of the different elements in the periodic table and of the different trends in the periodic table. Okay, now a last element is to consider the problem of diffusion. So we may expect the same thing. What would you expect in terms of carbon diffusion at the surface or in the volume of a given element as a function of carbon affinity? Would you expect carbon atoms to diffuse faster on the surface of an element having a high carbon affinity or having a low carbon affinity? It's a question. No idea? It's common sense in first approximation. So when you diffuse at the surface, you need the atom to go from one position to another. What prevents the atom from going to one position to another? This is the bond between this atom and the surface. You need to break this bond to move from one position to another. And in some cases, you even have to go through a higher energy state, like a barrier, to go to another more stable position. But in any case, the problem is to break, to lose, to weaken the interaction with the surface. So you would expect elements with a high carbon affinity, the elements that form very strong bonds with carbon, to prevent diffusion of carbon atoms. And then the diffusion constant of carbon on the surface of those elements or in the bulk of those elements should be very low. Okay? So this is kind of observed. You've got this same trend. High carbon affinity gives a lower carbon diffusivity, but it is more complex than previously, where we were just considering surface reactions. Here, if we consider bulk diffusion, it's not only the strength of the bond between carbon and the metal, which is important. There are other effects, because we want this carbon atom to move through a lattice, a 3D lattice of other atoms. Depending on the geometry of this lattice, depending on the size of the matrix atoms, depending on the size to go from one interstitial site to another, depending on the flexibility of this matrix. Are we close to the melting point, or are we very far from the melting point? These will give you an idea of how flexible the lattice is. Okay, so this is diffusivity is not just a question of chemical interaction. It's also a question about the geometrical, the type of matrix the atoms has to go through. Okay, so it makes things more complex, especially because different metals have different crystal structures, different crystal lattices. It can be BCC, it can be FCC, for instance. And you observe, for iron, there is a change of crystal structure at about 600 degrees C. I may be wrong, but this is the order. And you see that in BCC iron, the diffusion is much faster than in FCC iron. So it's not as easy as previously to give trends just as a function of the carbon affinity. Diffusivity is dependent on carbon affinity, but not only. At the end of the day, what we want for growing carbon structures is having a high mobility, the highest possible mobility for the carbon atoms to go to a low energy state, a very stable structure without defects. Okay, this is what we want. Okay, conclusion. Well, we need to take an element which has intermediate properties, not too high carbon affinity, not too low. We want something which is good for catalytic dissociation of hydrocarbons. This means high carbon affinity. We want something with high carbon diffusivity. It means low carbon affinity. We want something with an intermediate carbon-metal bonding to anchor the structure while together allowing integration of new carbon atoms. So we need also something with an intermediate carbon affinity. At the end of the day, experimentally, the best catalysts are found here in the middle of the periodic table. Iron, cobalt, nickel are the best elements to catalyze the growth of carbon nanotubes and graphene. Other elements around those, like copper, silver, gold, palladium, platinum, rhodium, and ruthenium, are also okay. They work, but usually you need to optimize the growth conditions for them to be sufficiently good, sufficiently active. Okay, with nickel, iron, and cobalt, they will be most of the time in any condition quite good. Okay, this is for the choice of the catalyst and the rationale for that. Okay, now we are going to move to more fundamental things concerning the growth mechanism. Before that, are there any questions about what was said before? I don't want to go too fast. There is a question here. Several questions. ¿Por qué? Cuando perpendicular. ¿Por qué? Ok. Ok. Okay. 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 So the question was about the interaction between nanotubes and the interaction between nanotubes and the substrate on the orientation. Is it does it have an effect on the orientation of the nanotubes? Alors, maybe I can go back to those pictures I presented at the beginning. Here. Here, for those two, the gas flow alignment and kite growth alignment, I already explained. It's a van der Waals interaction in this case with the support. So it's an interaction between the tube and the substrate that causes the alignment. Okay? No. Entre nanotubos. No. No entre nanotubos. Entre nanotubos y la membrana. Sì, il substrato. Because this in this case, this is different. This is different. Here, to get this alignment perpendicular to the substrate, you need a very high density of nanotubes. Why? Because you need a steric interactions between them. You need them to repulse each other in order to have no other choice than to grow perpendicular to the surface because of the steric interaction between the tubes. Okay, so in this case, this is a tube-tube interaction that allows to have the growth of tubes perpendicular to the surface. Okay? What?
Do you, with the steric interaction, are you talking about electrical? No.
When I say steric interaction, I mean direct contact between the tubes. Direct contact between the tubes. You do not have to consider electrostatic interactions. Okay. All right. Another question.
In this kind of synthesis, do you have catalyst remaining after you obtain the carbon nanotube? What do you do with that? About talking about the purity of the carbon nanotube.
Okay, so this is an important problem to remove the catalyst after the growth. So I do not plan to talk a lot about that, but there are different techniques to get rid of the catalyst after the growth. For instance, you can use acid treatment. Many acids can selectively remove metals like nickel, iron, cobalt without destroying too much carbon structures. Okay? This is the first way, this is the main way actually to get rid of the catalyst. The good thing with CVD is that the catalyst is at the beginning localized at the surface of the support. It means that at the end the catalyst is either mainly here or mainly here, but there is very little catalyst in between. Since the catalyst is localized, it's easier to remove it, okay, mechanically, physically, not chemically. On the contrary, for high temperature techniques, like those ones, those are just very good pictures. But usually, if you look a bit around, there are many metal particles everywhere. And here, it's really difficult to get rid of them because they are everywhere. Okay? When industrial? ¿Cuánto gramo? Okay, so the question is about the yield, the quantity of nanotubes you can produce with each technique. So, as I said, industrially, the only used technique now is CCVD. Here, things change very quickly because it's upscaled like every year. Let's say that you can make several tens of kilograms per day in some industrial setups. Like the largest ones using CCVD, like Arkema, like Bayer, those companies, they can make tens of kilograms per day. But they are very special machines, very different from those I have shown. For electric arc and laser ablation, you can make like a few grams per day, no more. Okay? So I go back to here. Now we move to the growth mechanism. So getting to more fundamental things, and we have about 20 minutes left. Yeah. Camilo agrees. Okay. So as I said, the growth mechanism, if we want to propose something realistic, has to account for experimental observations. So we can cite some important experimental observations. First, the best catalysts are nickel, iron, and cobalt. We already provided some good explanations for why those catalysts are the best for nanotube and graphene growth, thanks to their intermediate carbon affinity. Okay, then for multi-wall nanotube growth, you can grow them with catalysts at medium temperatures, but the interesting thing is when you use high temperature methods, you do not need a catalyst. Why is that? You need to answer this question. For SWINT growth, SWINT is single wall nanotube. Single wall nanotube, you need a catalyst in any case. Why is that? For graphene growth, there is also an effect of the catalyst on the number of layers, and you may wonder also why is that. So we are going to try to answer those questions by an appropriate mechanism. Okay, first thing, why is uncatalyzed growth of SWINT never observed? So to explain that, there was many simulations taking a tube with open ends here and heating it. And what people observed during simulations at high temperatures close to the temperatures actually used for the growth, is that this end will spontaneously close, as you see here, and another example is shown here. It means that an open end is not stable. If you increase the temperature, it will close by itself. This is the main explanation presently to explain why it is not possible to grow nanotubes, single wall nanotubes, without catalyst. You need something here to stabilize the opened end. Why is it different from multi-wall nanotubes? Again, the only answer we have is from simulations. People have studied multi-wall nanotubes. In this case, this is a double-wall nanotube. And they have studied if this open end is stable when you increase the temperature. They observe that in this case it is stable because there is an interaction, a stabilizing interaction between the two walls, as you observe here. And with this interaction, you are still able to incorporate new carbon atoms as shown here. This interaction is loose enough to allow new carbon to get in, to be integrated. So thanks to this tube-tube interaction, also called lip interaction, you stabilize the open end, and this explains, or at least is the best explanation at the present time, to explain why you can grow multi-wall nanotubes without catalyst, without a stabilizing catalyst, while on the contrary, with a single-wall nanotubes, a catalyst is required to stabilize the open end. Okay, so now I'm going to show you the best movie we have on nanotube growth. So to do that, I should try to go there. Okay, and I should start that. No. Okay. This movie is done by TEM, Transmission Electron Microscopy. It's also called environmental TEM because in the environment, in the gas phase, is put some carbon molecules. In this case, this is acetylene to be used as a carbon source. Okay, so in the gas phase, here are acetylene molecules. What you see is a metal particle, which is about 1.5 nanometers, and here is the support of the catalyst, which is in this case silicon oxide. We are now going to see what happens when you put acetylene in. So the movie is not, well, it's quite good quality for present standards. What you observe is a carbon cap starting to form and disappearing, or maybe being hidden behind. A new one appears now, but there's a cap, always a cap starting to cover the particle, and then it starts to be a bit longer. It covers partly the particle. You got the cap a bit longer. It seems to be stable, and now it's starting to be amplified. It gets longer and longer and longer and longer, and at the end we have a small nanotube. Okay? A question was, how do we do to record that? So it's in situ TEM, so you need a very special TEM allowing the introduction of gaseous molecules close to the sample. Okay, without breaking the vacuum you need in a TEM. So it's a very difficult technique. The temperature should be about 450 degrees C. No more. 450 degrees C. Okay. So, if we go back to the presentation, what do we see? What have we seen? We have seen different stages. I like you to bring up some conclusions. From seeing that, what is important to include in the growth model? Is there something that you were not expected, for instance? There are different ways to imagine the growth, and in reality, it looks like that. What is special? Have you something in mind? You don't get the question. So the question is not good. We want to build a model of nanotube growth. We have seen a movie of nanotube growth. What are the important stages? What are the important things we have to include in our model from seeing this movie? Nothing? Wait, okay. Lot of things. Okay, maybe a first thing, which were not expected by people at the beginning, is that the growth starts by forming a cap. It's not an obligation that the cap is formed at first. It may be formed later. For instance, the growth could start, as proposed by many people a few years ago, by an open end, not a closed end. And then later, this open end could close by itself. Here, it's not the case. The first stage is forming a cap. And this cap is used as a seed, as a nucleation seed for growing a longer crystal. Okay, like crystal growth. The cap is central. The cap is the seed of the nanotube that will grow after. The nanoparticle is moving, yes, in another case. Yeah, but you're right, it's important. What we have observed here is that the particle remains at the surface of the support. The tube grows above the particle. The tube does not grow between the particle and substrate. This is a special case. So this is something else we learn. Okay, there are other things we can learn, and from that we should propose a mechanism. And in this mechanism, we have first the formation of the particle, something we haven't seen in the movie, but that has to be done. We've got the particle on the substrate. We put some acetylene at the surface. It is dissociated. We got carbon atoms at the surface. And at some point, there's enough carbon atoms to make a first stable nucleus. And this is really an analogy to crystal growth. You know that in crystal growth, you need a critical size. There is a critical size of nucleus. Below this size, this nucleus, the seed, is not stable. You need to reach this critical size to start growing a larger crystal. So you need to reach the saturation of your solution, for instance. Then this cap will cover the particle. There is a template effect. We have seen this template effect. The cap reproduces the shape of the particle. This is really important. And then we got addition of more carbon atoms to amplify this seed. What we haven't seen, but we observe sometimes, is that there are defects included in the nice graphene lattice, like heptagons, pentagons. And then what we are going to see is that the growth starts by itself. The growth is not infinite. It will stop by itself after some time. And there are many reasons for that, and we are going to look at them later. Okay, Camilo said we had the particle staying on the substrate. It did not took off from the surface. It remains on the surface. Actually, experimentally, the two cases are observed. This case we have observed where the particle stayed on the surface and the tube grows, and this is called base growth. And there is another case which is also observed where the particle is detached from the substrate and the tube grows in between the catalyst and the substrate. And this is called the tip growth because the particle is at the tip of the tube. Okay? The choice between those two types of growth depends on the interaction between the metal and the support. If the interaction is really strong, if the metal particle is well anchored to the substrate, then it will remain there and we have a base growth. On the contrary, if the interaction between graphite and the substrate is stronger than the interaction between the metal and the support, then we'll have a tip growth model like that. So it depends on this interaction. The two exist. Okay, now to finish, we are going to talk about deactivation, which is also an important problem in heterogeneous catalysis, poisoning. This is really important when you do cracking of hydrocarbon molecules, for instance. It's important to say that at first, this is during cracking of hydrocarbon molecules, during reforming of hydrocarbon molecules, that those nanotubes were formed. It's very similar, except that in the cracking of hydrocarbon molecules, we want to prevent that because graphitic structures are poison for catalysts. Here, we want to grow them. So we want to grow them and at the same time prevent poisoning. But we are really at the frontier. We're in an extreme case where it's very difficult to prevent poisoning because poisoning can be due to the formed species. What do I mean? I mean that if we form too much carbon quickly, this carbon, instead of going away from the particle like a nanotube, could grow around the particle and encapsulate it. And then the catalyst is poisoned because there is no available surface. The surface is not available for new molecules to absorb. The surface is covered. It's unreactive. This is the first case of deactivation, encapsulation. The other typical deactivation of catalyst in heterogeneous catalysis is that the catalyst reacts with the support. The formation of silicides, the formation of silicates are very important problems in heterogeneous catalysis. So this is another kind of deactivation. Here, in the case of catalyst particle, there is another effect, another phenomenon, which is called Ostwald ripening, which is the fact that small particles are less stable than large particles, and the small particles will disappear and form larger particles. We will see that in detail. Just to show you that deactivation is real, this is a plot of the amount of nanotubes formed as a function of time. And you observe that for 3 different growth conditions. And you observe that at the end, the amount of nanotubes stagnate. You have no more growth. We have done nothing. It was just natural. Deactivation occurred by itself. Okay? It's self-deactivated. Okay? Depending on the conditions, you can have more nanotubes or less, but whatever conditions, there is always deactivation at some point. For those reasons. So, the first example of deactivation is what I said. The particle could be covered by too much carbon, an excess amount of carbon. You observe here, particle, and there is a thin layer of carbon around, and this is due to a too high amount of carbon supply. If you provide too much carbon to the surface, and this carbon does not move quickly into the tube, then it will react with other carbon at the surface. you will reticulate this carbon network, and then you will encapsulate the particle completely. Okay? So to prevent that, you should not supply carbon too fast. It means you should use partial pressure of carbon precursors quite low, not too high. At the same time, you should promote the fast mobility of carbon atoms at the surface. How would you do that? How would you improve the mobility of atoms at the surface? When a reaction does not go fast enough for you, what do you do? When los arepas are not cooked enough, when do you do? What do you do? You increase the temperature. That's the same. Here is if the migration of carbon atoms is not fast enough, you increase the temperature. Why? Because diffusion, surface diffusion, bulk diffusion is thermally activated. Okay? Not all processes are thermally activated, but most processes involving breaking chemical bonds are thermally activated. And as I said, migration of atoms on the surface means breaking bonds to move. Okay? So we can increase the temperature. So here, to prevent that, it's better to have high temperatures, to have fast migration of carbon atoms at the surface, and not provide carbon atoms too fast. Okay, now we move to other types of deactivations which are related to the support. And the first question is to wonder, what are the functions of the support? We already talked about the functions of the catalyst. Now, what are the roles of the support? Of course, it provides a mechanical support, stable, for the catalyst. Okay? We need something which is really stable, but means very inert at high temperatures in a very reducing atmosphere. It has to remain the same. We need something very inert. Also, we want to prevent what I explained previously. This is Ostwald ripening. Ostwald ripening may be promoted by the interaction with the substrate. We want to prevent that. Maybe in some cases, those who work on heterogeneous catalysis know that it's not only the catalyst itself which is important for the catalytic activity, but the support is also very important, because there is a strong interaction. There may be a strong interaction in terms of electronic interaction, in terms of chemical interaction between the small catalyst particle and the support. So it's very important also to consider this interaction on the catalytic activity. And of course, we want this support not to react with the catalyst, not to make alloy compounds like silicides, silicates, that would not be active anymore as catalyst. Okay, how to choose a good support? We saw that most supports used were silicon oxide, aluminum oxide. Why people chose silicon oxide, aluminum oxide as support? You all know that those oxides are very stable, especially at high temperature. Why is that? Again, we can use an Ellingham diagram to understand the thermal stability of those compounds. This time it's not an Ellingham diagram for the formation of carbides. This is an Ellingham diagram for the formation of oxides. For different elements, what do we observe? We observe that silicon oxide is somewhere, silicon oxide is here. It has a very negative free energy of formation. It means it's a very stable oxide. Aluminum oxide is somewhere here. Also, it has a very negative free energy of formation. It's a very stable oxide. It will be very difficult to reduce this oxide. On the contrary, if we look at silver, silver makes very unstable oxide. This is good for jewels, of course. It's better for that. It's very easy to reduce. Now we are going to use catalysts like iron, nickel and cobalt. We don't want them to be oxidized because as oxides there will be less active catalyst. So we want them to be reduced during the synthesis. So, is it possible? Iron is here. We have nickel here in blue. We have cobalt. Where is cobalt? Cobalt is here. Okay, so all of them are here. And you observe that they are quite unstable oxides. They are not metastable. They have a negative free energy of formation. So they are stable oxides, but they are less stable than the oxides used as support. It means that if I use hydrogen, this is this line, hydrogen. If I put hydrogen to make, if I want to make water, the line for hydrogen is lower than the lines for nickel and cobalt. What does it mean? It means that I can reduce cobalt oxides and nickel oxides with hydrogen. This is what we learn from this diagram. But I cannot reduce silicon oxide and aluminum oxide with hydrogen. This is in first approximation. It's not that simple, but it's already a good start, because since now I did not talk about the different concentration of hydrogen. Okay, I just said if I put in a closed volume hydrogen and silicon oxide, at the end there will still be some silicon oxide in the chamber. It's not possible to fully reduce silicon oxide with hydrogen if it's closed. But now if I use pure hydrogen in a continuous way in an open reactor, then I will have very little amount of water. Okay, so the inverse reaction will be very unfavored. So this is a question of modifying the equilibrium, displacing, shifting the equilibrium by playing on the partial pressures of the reactants, but also on the products of the reaction. Okay, so this is basic chemistry, but it's very important. So what does it mean? It means that if I shift the concentration, the ratio of hydrogen to water, the line for hydrogen will not be anymore this line, but it will be shifted to another line which will intercept this value, for instance, and this value. Okay, I'm not going into the details of Ellingham diagrams. This is not the purpose of this course, but it's to tell you that these Ellingham diagrams are very useful tool to know if you can do a special reaction, if the reaction will occur, if a special compound is stable or not stable in a given atmosphere, like a nitrogen atmosphere. And if you want to make a compound, if you want to reduce a compound, which partial pressure of reactant should you use? You can reduce metals not only with hydrogen, but with other things like carbon. Industrially, carbon and carbon monoxide also are used as reducers of metals. And you can use other lines here corresponding to the formation of carbon oxide, monoxide, dioxide, and so on. And it will tell you if you can reduce or not. Okay, so from this diagram we confirm that we need very resistant oxide supports like silicon oxide, aluminum oxide, magnesium oxide, titanium oxides. Those are good supports. And metal catalysts in standard growth conditions where there is a lot of hydrogen will be reduced. Most of them will be reduced. Okay, another deactivation process is reaction with the support. So I already mentioned that you can form alloy compounds like silicides when you put when you put a metal like iron or nickel on silicon and you heat it, then you will very quickly form iron silicides or nickel silicides because it's a very stable compound. To prevent that, because silicides are not good catalysts, you need to use a barrier like an oxide. Oxide is much less reactive than the silicon, and then if you use a silicon oxide, you can prevent the reaction between the metal and the silicon and prevent the formation of silicides, for instance. But you can also have other problems like diffusion in the bulk of the surface. So this has also to be taken into account. Okay, Oswald ripening, I'll not go into details of that, but it's a consequence of the Gibbs-Thomson equation that you see here. The small particles have a higher saturating vapor pressure than large ones. As a consequence, they sublimate, they disappear to the benefit of the large particles. This is the phenomenon called Oswald ripening. It can occur during the growth, and then the small particles disappear and the remaining tube cannot grow anymore because there is no more catalyst there. Okay, for graphene, I will not talk about that because I have not enough time, but it's a question of dissolution. The solubility of carbon is also an important characteristic of a good catalyst. If you dissolve too much carbon, then you will during cooling, the carbon will segregate and you will form new graphene layers. Okay, this is a summary of what I said here. It's no use that I read it. You will have the slides and you can read them afterwards. I thank you very much for this very nice opportunity to present this knowledge about nanotubes, graphene, and fullerenes. And now, do you have some questions? Some very last questions.
¿Hay alguna pregunta en Cumaná o en Mérida para el profesor Vincent Jordan?
Aló.
Sí, te escuchamos.
¿Escucha?
Sí.
Bonjour, Monsieur Jordan. Mes félicitations pour votre excellent exposé. Mais je voudrais faire une petite question concernant les méthodes de préparation des échantillons. Quel est le meilleur pour obtenir des nanotubes, un layer et un nanotube multilayer de purité bien haute? Car nous sommes intéressés de faire dopage avec des terres rares.
Okay. So the question is, what are the best preparation techniques if one wants to prepare either single-wall nanotubes or multi-wall nanotubes, and also obtain a good purity? And is it interesting to use lanthanides or rare earth elements? Oh, it's a difficult question. So using to get either single-wall tubes or multi-wall tubes is essentially a question of particle size. So it's not a question of the element, at least in CCVD. Most important is to control the size of the particles. So to control the size of the particles, you need to control the initial amount of catalyst on the support. This can be done by several techniques, like spin coating, like vacuum evaporation, like sputtering, like ion beam sputtering. So it's mainly about that. Then, because you can have catalyst coarsening, Oswald ripening on the surface, you also need to control the wetting of the catalyst on the support. So not only the catalyst is important, but also the support. So this is mainly about that. There are also additional things like small particles being more easily poisoned than others, but it's a second, I would say, it's a second order problems. Concerning the use of rare earth elements together with catalyst, I must say that I have really no idea about the positive or negative effects that it could have during CCVD. For sure, the use of lanthanides like lanthanum, yttrium, together with nickel, iron, and cobalt was very efficient for high temperature methods like laser ablation and arc discharge. But up to now, in CCVD, such elements were not found to be useful as additives. And as catalysts alone, they are usually not active. But this is also the case for high temperature techniques. So I don't know, it may be interesting.
Unfortunately, we have no more time to discuss, but we can discuss later with the people here. So I want to thank Vincent Jordan for this talk in the name of the ENANO 2011. And we will have a 15-minute break for a coffee, and then we will have Professor Cecil Sacri for the next talk. Desafortunadamente no hay tiempo de preguntas. Muchas gracias. ¿Qué es eso? Battery. Ah, hay que ponerlo a cargar. No,